when our next speaker is setting up, then I will introduce our next speaker, Professor Aleksander Madry. So Aleksander Madry is an associate professor in the ECS department at MIT. His research centers on arithmetic graph theory and understanding uncertainty in the context of optimization. Aleksander received his PhD from MIT in 2011. His work has been recognized with a number of awards, including a Sloan Research Fellowship, a number of Best Paper Awards at Fox, Soda, and Stock conferences. Welcome him.
Okay, thank you. Can you hear me?
Yeah.
And can you see my slides? Great. Okay, let's get started. So yeah, welcome everyone, and thank you for the invitation. So yeah, what I wanted to do today is talk about some of our group inquiries into trying to understand what do our models learn, and is it the right way to learn, or maybe not the perfect way to learn. So let's get to it. So the point of start here is our well-known current machine learning research pipeline. Okay, so the way things happen usually is that there is a data set that we know and love, like ImageNet, and then well, we train a model on this. And of course, the way we know whether the model is good or bad, well, there is some test set that was held out and unseen that we test the performance of the model on, and kind of the corresponding, this gives rise to a benchmark that kind of in which we want to evaluate how well our model is working. Okay, of course, this is not a one-shot process. So essentially, whenever we train a model and we see how well it does, well, we learn something from this, and then we try to tinker with our model to get the performance better and better, and kind of this cycle of improvement leads to better and better performance on our on our benchmarks. Okay, so this is kind of how from a bird's eye view our research the research machine learning can be viewed as. And of course, there's a bunch of things that when we look at this and we work on this, we should and are concerned about. Okay, so one of the most obvious things that we worry about is this, I would say, classic overfitting. Okay, so essentially the thing is that, well, I train my model on this data set, on the training set of my data set, which I can do whatever I want on, and then I would like the performance on this training set to extend to this unseen test set. Okay, so this is the whole question of, okay, are we maybe memorizing the training data, or are we learning it in a non-generalized manner? And this is what classic machine learning was focused on and made many advances, to try to counteract this possible worry. Okay, so that's one concern, but not the only one. So the other one that kind of came to realization a bit more recently because of actually all the progress, and it's a bit more subtle, is this question of adaptive overfitting. Okay, the question is that actually, this deployment of a model is never a one-shot process. We always, when we see the performance of our model on this test set, we kind of use this information to try to improve how the model does. And kind of as a result, technically this test set, since it's a fixed test set, it no longer is unseen. And over time, you will be worried that maybe we are doing an analog of p-hacking here, that kind of we figure out, we tune our framework to do well on this particular test. Okay, and that's what adaptive overfitting is about. And people worry about this too. And we will talk about it later a little bit more. But what I want to talk today is yet another concern that actually maybe people don't seem to think that much about, although I would lie if they said people don't think about it at all. And essentially what it has to do is, it is based on this realization that, as much as we like to focus on this data set model accuracy kind of triangle, there is one other big element that is part of the system, namely whenever we create a data set, it's always to view it as an abstraction or a kind of a way to capture some actual real world task. So for ImageNet, you could view it as an object recognition in the wild, as essentially the real world task that you really would like to solve. And ImageNet is just a way for you to try to train models that solve this real world task properly. And essentially, once you realize that there is this kind of additional element, and actually you in the end you care really about this element to perform to be solved well, then essentially you start to asking yourself, okay, so as much as we can make sure that this triangle of dataset models and test accuracy kind of works the right way, how do we know that maybe we are overfitting to this whole benchmark? essentially, instead of trying to make progress on the original real-world task, we end up making progress just on this triangle, kind of this evaluation, like this way we evaluate the model and the way we kind of this proxy version of the task we really care about. Okay, and that's something I want to focus on today. And kind of, so the question is, how well do our data sets reflect the real world? In particular, what dataset biases do models pick up? And how are these biases introduced? Like by bias here, I mean kind of what kind of things to learn that are in the dataset are actually not generalizing to the real world task that the given dataset was supposed to model. Okay, so let's dig in. So the point of start here is probably like the simplest setting, the simplest type of bias you could think about in the context of computer vision, namely background bias. Okay, so essentially how much backgrounds are incorporated into the decision process of the state-of-the-art model. So essentially, like, well, the first question you would ask yourself, okay, so is there even a signal in backgrounds? And you can just run simple experiments, and it's easy to see that the answer is yes. That it's not only that there is signal, but our models can definitely extract it if asked to. But of course, this alone will not be too shocking, because also humans can use backgrounds, and actually there definitely is signal in the background. Like sometimes it's easier for you to recognize a person if this person appears in the right context. So essentially, if my work colleagues appears like I see him or her at the vacations, like in some resort, it might take me a moment to realize who that is. So this is definitely not surprising by itself. And what we really wanted to do, and that's essentially what our recent work with my students was about, is trying to get a bit more fine-grained understanding of what exact nature of this dependency is. Okay, so to this end, what we did, we essentially create various versions of like mixes of like when you kind of like data sets, like versions of the original data set in which you only keep the foreground picture, foreground object, or you keep a foreground object and kind of overlay it on top of different backgrounds, either coming from some other image from the same class or maybe image from a different class, or sometimes you just show backgrounds alone. Essentially, we have this like different data sets to kind of try to pinpoint exactly like what from the background are our models using and leveraging, if at all. Okay, so I will not be able to give you like a full overview of what we found, but like the one general finding is that in general, kind of model accuracy is significantly reduced when kind of the background signal is not kind of like is not fully in sync with the foreground object. And some of this is of course part of just the artifacts of our way of combining the backgrounds, but it turns out that there is more to it than that. But one finding that I wanted to bring your attention to is so-called adversarial backgrounds. So it's not only that the models do depend on backgrounds, in the classification, which again is not surprising by itself. It turns out in some ways you could claim they are overlying on it. Essentially, like what is possible is that for a vast majority of images, you can fool the model to think that the classification of the image is of the foreground object is different to what it should be by just choosing an adversarial background for it. And in fact, there are some background, and here are some examples that like they work for a large fraction of images to essentially to like for a large fraction of foreground objects to fool the model into believing that the class that is correct for this image is the background class as opposed to the foreground class. Okay, so this is kind of a worrying. Again, it's okay to to rely on backgrounds to get a better a better classification, but if it's so misleading that it can completely like make us not pay attention to the foreground image, foreground object, there is something to be fixed there. And this is kind of the next question that we kind of ask here is kind of like, can you get more background robust models? And it turns out that the answer is yes. One natural way to do it is just to randomize the backgrounds during training. And it does help, but also it decreases the base accuracy because essentially like, well, the signal of the background that was useful for classification before is no longer there. So somehow you can't really get the top performance anymore when you do that. And the other thing we looked at is essentially we looked at the progression on like, as we improve our models in terms of like, let's say ImageNet accuracy. So we looked at like different like state-of-the-art models at different points of time. And we wanted to understand, how this reliance on backgrounds, in particular vulnerability to adversarial backgrounds, how does it change over time? And the good news is that in general, like as our models get more accurate, they also become more background robust. Although interestingly, it doesn't mean that they don't rely on backgrounds. They do rely on backgrounds, but they are less likely to be fooled by the adversarial background. So essentially, like, things are going exactly the right way we would expect. Okay, so this was just just a simple example of like how to study particular biases that come from the way our datasets are created. Like as a human, you know that it's all about the foreground object, and the background could help you, but if you know what the foreground object is alone, you should not be using backgrounds. For the model, this is completely unclear, and that was the evidence we have seen. But this was just an example of a bias, and by far it is not the only one. So what are maybe some more subtle kind of biases that come into our model, in our data sets, and also where do they come from? Okay, so essentially, so let's just start. So what kind of biases could be there? So what we have over here is just 3 examples of ImageNet inputs, and here are ImageNet classes that actually correspond to these images. Or do they? So actually, I lied to you a bit. So actually, these classes I provided here, they actually are not the correct ImageNet labels. The correct ImageNet labels are the ones in red. And you might say, well, essentially, you can ask, okay, so yeah, we were wrong. We are not good at ImageNet yet, and maybe our knowledge of dog breeds, it still needs kind of improvement. But the other reaction, if you kind of look at what's happening here, you might see, okay, but where this answer is really wrong, is it really so obvious that this is a church? Like the picture on the left is a church and not a monastery? Not really. So there is something going on here, that kind of these labelings might be kind of have some biases and kind of counterintuitive leanings towards one class versus the other. And kind of we wanted to dig a bit deeper into trying to understand, what might be the problem here and how much of a problem is that. Okay, so to kind of understand even why these biases might be happening and why we might want to ask these kind of questions, well, we should think a little bit about how our datasets are created. And yes, usually when you think about how our datasets are created, you kind of have this image in mind that, okay, there's a large collection of real world images, and then you just pass it to some expert annotators that figure out the perfect class for each of these images, and kind of that's how the ground truth label is created. So this is kind of the idealized view that we actually would like to believe this is the case. But if you think about it for a moment, you realize that this kind of approach just does not scale to millions of images like ImageNet and thousands of classes like ImageNet. Okay, so this will just not work. So what do people actually do in practice? Well, one of the popular approaches in practice just works as follows. In particular, this is the way the ImageNet and some other large-scale vision model datasets are created. So you kind of first figure out what will be the kind of structure of classes that you want to even have, and maybe you use WordNet as a seed here. And then what you do is essentially for every class that you want to have, you just use search engines like Flickr or Google image search to find essentially you plug in this class name or its variations, and you look at all the images that you will get back from this. And then of course, you expect that most of the images are indeed examples of this class, but you want to have some validation, and you kind of run this crowd-sourced validation, which essentially in the context, for instance, of ImageNet boils down to essentially showing, the image to a human and asking, does this image contain an object of class X, where class X is the candidate label that corresponded to the search term that you entered where you retrieve this image. Okay, so this is a nice way to do it, and actually definitely scales much more nicely than the idealized approach. But as much as it works and it gives us very interesting and useful models, it has kind of a problem. And the problem is that essentially, if you think about it, for every fixed image, we always have a candidate label, and all we are asking the human validator is this a possible label for the given image? And we ask them this just for this only one single candidate image, a candidate label, and also we ask it in isolation. So the annotator might not even be aware that there could be other possibilities for the class. So there's just a very leading question like that. So this is kind of the problem. And in particular, you can see now why the images that I showed you before might kind of got these different labels, just because the seeds, the image was retrieved for the query church as opposed to monastery, and then to humans, either one would work, so they kind of validated the one that was given to them. So, so okay, clearly something can go wrong, but of course the question, and this is the, kind of the motivating question for our recent work, is to try to understand, how much of the problem this really is in ImageNet. Okay, so to what extent this kind of biases coming from this validation process actually could, distort, the kind of the biases and the performance metrics that we currently use, for instance, to evaluate ImageNet. Okay, so of course, to be able to, to answer these kind of questions, well, we need to first have some detailed annotation. Like we need to have some better notion of ground truth to compare it against, what is currently in ImageNet. And that's what we want, that's what we embark on first. And of course, ideally, what you would like to do, you would like to just show, example ImageNet images to people and ask them, okay, now classify, each object in the image. So first of all, you actually recognize the possibility that there might be more than one object in the image. And then you can ask them, classify, each of these objects by, like assigning it to one of the 1,000 possible classes. So that's what we would like to get. This way we would get this like more fine-grained, more dense annotations for our images. But of course, again, this is not feasible. Like we can't people to realistically be able to navigate 1,000 classes to begin with. So what we did instead is kind of the following simple but actually surprisingly useful idea. Is what we did is kind of try to kind of pull top 5 predictions from a variety of different models, just to kind of get a diverse set of proposals. And essentially, based on that, we got a narrowed down set of even possible classes to consider for a given image. So instead of having, confronting the annotators with 1,000 classes, in the end, they end up being confronted with 8 possible classes, like for any of the objects that might be appearing in the image. Okay, and so the kind of task that they are asked then for is just the following. So okay, here are some, let's say in this picture are 3 possible classes that may be relevant for this image, and they just essentially have to say which one are valid and also which one is the main object according to them in this image. Okay, and the important thing is that they have they are explicitly made aware that there can be multiple labels that are valid, and they have to really think about this question of the main object as well. So this is the kind of questions we ask. Then we aggregate this over worker, and essentially like what we get out of this is this kind of nice annotations of like for an image, like what are all the objects in there, like how many objects is there, what kind of labels are valid for each of these objects, and also what is the main object as viewed by annotators here. Okay, and this is exactly the kind of information that you would need. And kind of like, we really like this procedure because you can view it as a like bootstrapping the ImageNet annotations. Like in some ways, now that we have this initial labels in the ImageNet, and then we train model based on them, actually like, we can view it as some way of aggregating all of this insight that were kind of, provided by this collection of images plus labels. And now we are kind of doing the second run step using annotators again to just like refine and kind of sharpen these predictions and make them more fine-grained. So I think this is kind of, this procedure could be used for other data sets as well and for other purposes as well. Okay, this is what we did. Now the question is, as long as we have these annotations and we did it just for 1/5 of all of the validation set of ImageNet, we can now ask questions. Okay, how accurate ImageNet labels actually are once as confronted against this ground truth. And there's a bunch of findings, and again, you need to look into the paper to see all of them, but I just want to bring attention to some of them. So one of them is that indeed this multi-object images is not something that just happens to happen from time to time in the ImageNet. Actually, like 1/5 of the images we labeled, and they were like random images from the test set, contain more than more than one label. Okay, so it's like this multi-object nature of this images is actually something that applies to a large fraction of the test set. Okay, so this is just an example. This is honestly an extreme example where there is like multiple valid objects. But again, like just if you ask for 2 objects, there's plenty of images like that. And now what happens is, okay, you can just wonder, like, if there are like at least two possible correct answer for an image, then like how does it how does it kind of relate to the top 1 accuracy? So that's what we wanted to do. So essentially what we plotted is just we looked at the accuracy on the full test set, which is kind of our current measure of quality of a model, and we confronted it against the accuracy on the subpopulation of images that are single object versus images that are 2 or more objects. And what we got is kind of the plot on the right. And essentially like this plot, in both cases, we see improvement over time. So better models are doing better on both of the subpopulations, but you see that there is like a large performance drop, like 10% performance drop between the performance on the multi-label images versus the single label images. Okay, and now you might say that maybe just these images are hard, but this turns out to be that actually that's not the case. So essentially, like if we now count a prediction for this multi-object images as a correct if it matches any of the objects according to our annotators that is present in the image, then essentially we are getting this curve over here, which essentially shows that this drop in performance essentially disappears. So essentially, like the major driver of like performance loss on this kind of images was just this fact that they were ambiguous, inherently ambiguous. Okay, so that's interesting. And of course, again, but now we can dig a bit deeper. So once you know that the objects, that the images can have more than one object, you can ask yourself, okay, so which, like if there's many objects, maybe like which object does the ImageNet label correspond to? And your hope would be that like most of the time, or always, it would be the object that is kind of main in the image. This actually turns out not to be the case. So essentially, like often the image that is viewed as the main, like the main in the image by an annotator is not the one that the ImageNet label corresponds to. So it's essentially like in general, this like ImageNet labels tend to focus on like very specific kind of very distinctive object in the image. So here are just examples. So in the middle example, kind of, even though obviously probably our instinct would be that this is about a suit, to an ImageNet model, like they like the fact that this is a bow tie, and probably this is just a bias coming from the way the search engines, search engines work, where kind of this is something that probably you would get if you enter the bow tie into the picture. Okay, but kind of the labels a priori do not try to be as general as possible. They just like whatever works as long as it's a valid labeling. This is it. So actually, like there is a problem that the main object is often not the ImageNet label. So that's really a problem. But what is interesting is that actually models kind of seem to be aware of that. And they seem to pick up on these dataset biases. And they actually realize that like on this middle image, you actually should be talking about the bow tie as opposed to a suit. So kind of, in some ways, instead of like having like 50-50 chance of getting the right class, they actually do realize what ImageNet is really means in this image, and kind of they are extracting these biases there, even though no, this is clearly not what we would intend to have. Okay, so this is kind of one type of insight. The other type of insight you may ask about is saying, okay, so now that we have this like more fine-grained annotations, we can ask ourselves, okay, so how good ImageNet models really are? Okay, once we take into account all these issues with labeling, and you can just do this kind of human-based evaluation in which you look at the prediction of a given model on a given image, and instead of saying it's right and wrong or wrong by just confronting it with the ImageNet label, you can actually ask humans, okay, is this classification actually a valid classification for this image? Okay, and what do we find? And what we find is like from this point of view of metric, again, as we improve, over time on our like ImageNet benchmark, the models improve on this metric as well. But essentially what is interesting is that somehow, in some ways we seem to be hitting this non-expert annotated baseline. Like in some ways, currently, if you look at the incorrect predictions of models and ask the humans how incorrect they are, they honestly often are not able to take to tell the difference between this incorrect prediction versus the correct ImageNet label. So in some ways, kind of our models might be already getting to this baseline, which probably is the best we can hope for, currently, and pushing them to get even better accuracy than that might actually lead them to have to force them to overfit to the biases of the dataset, as opposed to getting better at the task that you want them to be good at. Okay, so that's kind of a very interesting, thing that like we realized, and kind of it shows that we should be careful, like as we try to push the percentage on the ImageNet accuracy further and further. We should be really careful if we are not asking for too much, and as a result we will distort the the progress that we are making. So this is kind of what I wanted to say about this benchmark versus dataset alignment. But I just wanted to come back quickly to this adaptive overfitting because it fits the story of biases in a nice complementary way. So essentially, like, as you remember, like kind of the adaptive overfitting was all about this kind of avoiding p-hacking. So essentially saying, okay, if we have a bunch of different researchers and different models that evaluate themselves on the same test set, maybe we end up, not making as much progress as we think we are, because we are essentially overfitting to this particular test. So one way to measure it is kind of this idea of dataset replication. And the idea here is exactly to say, okay, so if we are worried that we are overfitting to this particular test set, how about we create a new independent, like a new test set that is trying to like match closely the underlying distribution, but be different to the test set that everyone kind of compares themselves to, and see how the performance on the original test set transfer over to this new test set. Okay, so this is kind of this really neat idea of like how to try to diagnose this problem. And indeed, in particular, Rect and all like were, pioneered this by kind of looking at the, ImageNet dataset. So they create this ImageNet-v2 dataset. So yeah, so they started from the ImageNet, and kind of what they wanted to do is they wanted to source new Flickr images, because Flickr is largely where ImageNet images are coming from. And they kind of course, they can't just take a random subset of, of Flickr images, because, the Flickr images that made into ImageNet were selected, for quality in some way. And essentially the kind of the way they were selected for quality corresponded to a metric called selection frequency. And what they wanted to do, they wanted to get a new subset of Flickr images that control for the selection frequency as well. Selection frequency is just roughly the question is that if I show an image and I ask you, is this an image from this class? How often will an annotator say yes versus no? And kind of course, so what you would hope is that, the better selection frequency, you actually like have a better quality image. The lower selection frequency, this is a lower quality image. And what you would like to do is you would like to make sure that, you have some threshold, and kind of the images you take are the ones that are in general have a large selection frequency. Okay, so that's kind of the intuition. And what they did is kind of they set up a pipeline that essentially tries to match the selection, like measure selection frequencies both for the the sourced Flickr images and for the original test set, and they have to remeasure it because we don't have access to the selection frequencies that were used at the time when the ImageNet was created. And what they do is that they essentially just match the empirical selection frequencies they find to kind of make sure that this new test set has the same distribution as the old test set. Okay, so that's what they did, and that's how they got the new test set. And essentially now, what were the results that they got? Well, essentially they get like two kinds of findings. So the first kind of finding was that actually they did not find evidence for adaptive overfitting. So that's a good news. But what they also found that there is a significant accuracy drop in the performance on the new test set as compared to the original test. So this is bad because it suggests that our models are kind of brittle to this kind of distribution shift that underlines this problem. And and now it's natural to ask, okay, so but where is this? Why is this new data set harder though? Like what makes it, like why our models that worked well on tests on the original test set seem to perform so much worse on the new test set? And that's something that kind of we wanted to take a look into a bit more, because it's important to understand, where this kind of accuracy drop is coming from. And what we discovered that actually like one possible explanation of like at least a large fraction of this, of this drop might come from a statistical bias, like a subtle statistical bias that actually this creation of this new test set actually entailed. And essentially, like if you remember, like all that the new test set was trying to aim, it was trying to match the selection frequency distribution of the original test set. But the problem was that like selection frequency is just an idealized thing. Like this is just something that we like think about, like if we had infinite number of annotators trying to like, and we would ask each one of them about this question. And of course, in reality, we cannot afford to ask infinite number of annotators. We only ask a finite number of them, and usually a small number of them. And as a result, this reading of the selection frequency ends up being noisy. And of course, for a given image, this reading is actually an unbiased estimator, which is fine. But it turns out that the way we do the matching actually leads to a systematic bias that is kind of not unbiased anymore. And essentially, like as a result, what we show is that it makes the images that end up in this new test set to be actually be harder than the ones that were in the original test. And essentially, like how can you now try to validate this hypothesis? Well, one way what we did is just we essentially used statistical modeling to try to correct for this bias. And I will not get into details of how we do it, but the point is that once we kind of do that, then essentially like this drop reduces significantly. It goes down from like 11.7 to 3.6%. So it's still there. So there's still something to understand, but at least it's like significantly reduced. And we get, similar results also with, with other techniques. Okay. So that's all I wanted to say. So let me just conclude and just say a few words towards the end. So first of all, I think the message that I want you to have is that like what models do and do not learn is not always clear. And we really should be careful about studying it if we think about, trying to drive our field by pursuing benchmarks, in particular, if we think about robustness. And essentially, like, the models are affected by both the biases in the world, but also biases over dataset pipeline. But, we can improve the situation if we kind of recognize these biases and we account for them. So going forward, the question is, what other biases do our models learn from the data? How do we train the models so they avoid learning or relying too much on these biases? And essentially, like, how do we measure performance on the underlying task we care about, meaning it's like real world object recognition, if we always need to, in the end, project it down on some particular benchmark? So thank you. And and I think I will not be answering questions now, but there will be a session where I will be answering questions.
Yeah, so thanks a lot for your presentation.
Yes, so yeah, I will just stop sharing.
Yeah, thanks.